Ladies and gentlemen, please welcome. This is our 8th seminar of this academic semester. If you remember, last week we started with theory of probability, and we continued with the calculation of random variables. Yes, theory of probability and random variables. We calculated some examples. And today we will continue. We will continue with discrete random variable, because you know that random variable is divided to discrete and continue. Yes, discrete random variable is a little bit more easy because we are able to use classical operators of summation, for example, yes, because there is a finite number of possible values, yes, which can be included in the range of the discrete random variable, but continuous random variable has infinity options, infinity values in the set of range, yes, of this random variable. So we must use the Newton integral as the integral calculation for this continuous random variable. So today, discrete random variables, continue random variable, and we will start with the probability distributions. So we can start. Okay, the random variable x has a probability function. So there is a formula, yes, a mathematical function of the random variable x probability that random variable x will be equal to x is equal to 6 minus x divided by 15. 6 minus x divided by 15, and this is valid, yes, this is valid for discrete values 1, 2, 3, 4, and 5, yes, and probability is equal to 0 in all other cases, yes. If the value will be different than 1, 2, 3, 4, or 5, yes, probability is equal to 0. Write a probability function in the table form. So we have here, yes, this function px, probability that random variable x, yes, will be equal to x is defined by this expression 6 minus x divided by 15, yes, and I would like to create a table where is variable x equal to 1, 2, 3, 4, and 5, yes, and I would like to calculate these probabilities, the values of this probability function. So what I have to do, I must calculate 6 minus 1 divided by 15, 6 minus 2 divided by 15, 6 minus 3 divided by 15, 6 minus 4 divided by 15, and 6 minus 5 divided by 15. Yes, so I must calculate these 5 partial values, and values will be written here, yes. So 6 minus 1 divided by 15 is equal to 0.333. I will use only 3 decimals, yes. 6 minus 2 is 4 divided by 15, 0.2 2, 6, 7. 6 minus 3 is 3. 3 divided by 15 is 0.2. 6 minus 4 is 2. 2 divided by 15 is 0.133. And 6 minus 5 is 1 divided by 15 is 0.067. Okay, so this is the probability function in the table form. It's necessary to know that if you calculate the summation through all x, 0.333 plus 0.267 plus 0.2 plus 0.133 plus 0.067, result must be 1.000. Yes, because in your formulas you have written that summation through all x of px must be equal to 1. Yes, 1 or 100%. Yes, if you multiply these values by 100. Yes, so this is the probability function. We will write also the distribution function fx. Yes. Distribution function is created by cumulation of probabilities. Yes? Do you remember the cumulation of relative frequencies in descriptive statistics? 0.333 plus the value on this position. Yes, so 0.333 plus 0.267 is equal to 0.6. And we can cumulate. Yes, we can add other values. Plus 0.2 is equal to 0.800. Plus 0.133 is 0.933. Plus 0.076 is 1.000. So this is the distribution function fx. Yes, given in the table form, yes, calculated on the basis of probabilities. And now we would like to calculate the mode, yes, the mode, expected value, the mean, the variance or dispersion of this random variable x, and standard deviation. So we will start with the mode. Yes, the mode. What is the mode? X with hat. Yes, the mode is the value of the random variable with the largest probability, with the highest probability. So in this situation, yes, the mode is equal to 1 because value 1 of this random variable has the largest probability, 33.3%. Yes, so this is the mode. Expected value of random variable x, yes, the average, the mean, is calculated according to your formulas like summation through all x, x times px. Yes, so what is necessary? What is necessary to calculate? We must calculate multiplication x times px. Yes, another column. And after we calculate this column, we must calculate the summation. Yes, summation of these values. So 1 times 0.333, 2 times 0.267, 3 times 0.2, 4 times 0.133, and 5 times 0.067. Yes, please be careful. You must use probabilities, so you must use these values. Yes, not values from the distribution function. So you know that multiplication has bigger priority than summation, so you must you can write directly on your calculator these partial values directly on one display. Yes, 1 times 0.333 plus 2 times 0.267 plus. Yes, because multiplication has bigger priority than summation, so you can write it directly on one row, press enter and you will see result. Yes, 3 times 0.2 plus 4 times 0.133 plus 5 times 0.067, enter. 2.334. Yes, so this is expected value of the random variable x. Yes, expected value. You can imagine, yes, for example, that random variable x, yes, from 1 to 5 is the grade from midterm test of mathematics, for example, at the secondary school. Yes, midterm test of mathematics. You have grades 1, 2, 3, 4, and 5, yes, and there you have probabilities. Probabilities, yes, that the student received the grade 1, probability that the student received the grade 2, etc. Yes, the model grade, yes, the mode is 1. Expected value, the average of the classroom, yes, is 2.334. Yes, so this is expected grade, expected value, and we will calculate variance. Variance, in your formulas, you have written variance of random variable x is equal to, there is summation through all x squared times px, yes, minus, and here in squared parenthesis we have summation through all x times px, this is squared, yes. So this second part, yes, is already calculated because here in this squared parenthesis you have expected value squared, yes. So this value 2.334 squared. But I must calculate this first part, yes. I must calculate here x squared times px, yes. So x squared 1, 4, 9, 16, 25, yes, 1 times 0.333, 4 times 0.267, 9 times 0.2, 16 times 0.133, 25 times 0.067. Okay, so again, I can calculate this directly because multiplication has bigger priority than summation, yes? Okay, so please check this calculator. 1 times 0.333 plus 4 times 0.267 plus 9 times 0.200 plus 16 times 0.133 plus 25 times 0.067. Enter. So 7.004. Yes. So this is this first part. Yes. This first part in the variance formula. So the variance, yes, the variance of random variable x will be calculated like 7.004 minus second power of expected value 2.334 squared. Yes, so this value minus 2.334 squared is equal to, variance is equal to 1.556444. Yes, so this is variance of this random variable because we try to imagine that this our variable x is the grade on the elementary or high school, yes, from the midterm test of mathematics, yes, we can calculate standard deviation of random variable x, which is calculated like square root from the variance. So square root from this value 1.556444. Yes, and standard deviation is a grade, yes, in basic units. This variance is in squared units. We are not able to interpret this value, yes, but square root from this value 1.2476, yes. So this is measured in grades, in marks, yes, from the test of mathematics, yes, midterm test of mathematics at the elementary school. So this was random variable, yes, random variable x. Expressed by probability function. We calculated probabilities, we calculated the values of the distribution function, and we calculated the mode, expected value, variance, and standard deviation. We will continue with another example, yes, another example. Now we don't have here the function. We have already calculated values of probabilities, yes. So again, you can imagine, yes, you can imagine that we have here the grades, yes, from the test of mathematics. Grade 1, 2, 3, 4, and 5, yes? And there is probability that student received grade 1, 0.15, student received grade 2 with probability 0.25, yes? 0.50 is probability that you will receive the grade 3, 0.09, and 0.01, yes. There is also calculated summation through all x, 1.00, so everything is all right, yes. And what can we do? Calculate mode, expected value, variance, and standard deviation. So the same like in the case of previous example, yes. So what is the mode? Mode is the grade, yes, with the largest probability in the sample. Yes, so this is x hat. This is the mode. Yes, the modal grade. The modal grade is 3, grade 3 with 50% probability. Yes. For calculation of expected value of random variable x, you must calculate summation through all x times px. So you need this another column where you must calculate 1 times 0.15, 2 times 0.25, 3 times 0.50, 4 times 0.09, and 5 times 0.01. And summation will be expected value. So you can do this 1 times 0.15 plus 2 times 0.25 plus 3 times 0.50 plus 4 times 0.09 plus 5 times 0.01, 2.56. Yes, so this is average grade, average mark, yes, from test of mathematics. And for dispersion, for variance, yes, Vx, I need to calculate summation through all x squared times px, yes, minus squared parenthesis, and there is expected value squared. Yes. Okay, so this part will be calculated here. So squares of variable x, 1, 4, 9, 16, 25, yes? Okay, times probabilities, yes? You must use probabilities, yes? Not anything else. So 1 times 0.15, 4 times 0.25, 9 times 0.50, 16 times 0.09, and 25 times 0.01. Yes, so this part will be calculated here. 1 times 0.15 plus 4 times 0.25 plus 9 times 0.5 plus 16 times 0.09 plus 25 times 0.01, 7.34. Yes. Okay, so now we can calculate the variance. Yes, we can calculate the variance. It will be calculated here. For example, variance of the variable x is equal to 7.34 minus expected value 2.56 squared. Yes? Okay, so 7.34 minus 2.56 squared. This is equal to 0.7864. Remember, yes, this is variance. Yes, this is variance. So this must be non-negative value. Non-negative value every time. Yes, this is positive value, small but positive. So it's okay. Yes, but this mustn't be negative, yes? It can be equal to 0, but never negative, yes? And because this is in squared units, we are able to calculate standard deviation of random variable x, which is calculated like square root from the variance, 7864, yes? And the standard deviation will be in basic units, yes? So square root from 0.7864, enter 0.8868. Yes, so this is standard deviation, and what else? So we calculated mode, expected value, variance, and standard deviation. Now we would like to calculate probabilities. Yes, probabilities. So probability that random variable x will be equal to 4. Yes. It's not necessary to calculate, it's enough to find the value in this table. Yes, probability that random variable x will be equal to 4 is 0.09, and this is 9%. Yes, this is 9% probability. We can continue. What else is written here? Probability that random variable x will be higher than 1 and smaller or equal to 3. So what this means, this is probability that you will receive grade 2 or probability that you will receive grade 3. Yes? So again, you can calculate a summation 25% and 50%. Yes, 0.25 plus 0.50 is equal to 0.75. So this is 75% probability that you will receive grade either 2 or 3. Yes. And finally, we can calculate probability that random variable x will be higher than 1. Yes. Okay, so this can be calculated like 1 minus probability that random variable x will be smaller or equal to 1, yes, because what is it higher than 1? 2 or 3 or 4 or 5, yes? So 1 minus 0.15, so everything worsen than 1, yes? Probability that you will receive everything worse than 1, so either 2 or 3, either 2 or 3 or 4 or 5, yes? And the result is equal to 0.85, and this can be interpreted like 85%, yes? 85% probability. And finally, we will finish this example with distribution function. Write the distribution function of the random variable x in the table form, yes? In the table form. So there is px, and there I will write fx, yes? Fx, distribution function of the random variable x. So on the first position, we have 0.15. Yes. On the second position is 0.15 plus 0.25. So there is 0.40. 0.40 plus 0.50 is 0.90. Plus 0.09 is 0.99, and last value 0.99 plus 0.01 is 1.00. Yes, so there is the distribution function in the table form. Do you remember example 7.3 about the sports shooter? Yes, our example 7.3 sports shooter, yes, it's the target every shot with probability 80%. So we'll use data from example 7.3 and we'll specify the definition range And we will write a probability function for the random variable x. What is the number of shots scored in 5 attempts? Yes. So what is necessary? What is necessary for us? We know that n is equal to 5, yes, because we had here this target with 1, 2, 3, 4, 5, yes, 5 positions. So we have here 8 independent attempts. Probability that shot will be in the target is 0.8, and probability 1 minus p that shot will be out of the target is 0.2. Yes, so we know that x, yes, is equal to either 0 or 1 or 2 or 3 or 4 or 5, yes? 0 shot in the target, 1 shot in the target, 2 shots in the target, etc. until 5 shots in the target, yes? So this is our definition range, yes? This is our definition range. And now we would like to create a general formula for the calculation of probabilities, yes? If you remember, we had combination number n above x, yes? And we multiplied this combination number by probability, by p-value probability, powered by x, number of shots in the target, yes? Our variable x is number of shots in the target, yes? Number of shots in the target is our random variable x. So n above x combination number times probability that shot will be in the target powered by number of shots in the target. And there was multiplication 1 minus p, yes, and this was multiplied by n minus x. In our situation, 5, yes, attempts minus number of shots in the target. Result is number of shots out of the target, yes? And we would like to create this function in general. So one equation with one unknown. Probability that random variable x will be equal to x is equal to n is constant, yes, 5. There is every time value 5 because we have 5 attempts. 5 above x. Multiplication probability 0.8 powered by x times 0.2 powered by 5 minus x, yes? In this equation, you have only one unknown variable, and you can use this function, for example, in Microsoft Excel, yes? Definition range, x is equal to 0 or 1 or 2 or 3 or 4 or 5. And this probability function, px, is equal to 0 in all other cases. Yes? So this is our general probability function. In this table, yes, there is the distribution function of the random variable x, yes, and we would like to write a probability function px of this random variable. So you can imagine that variable x, yes, is for example what? Spend money in the supermarket, yes, 100 euros 150 euros, yes, 300 euros, and 500 euros, yes. So spend money in the supermarket or in some store, yes, and distribution function of this variable x is here, 0.15, 0.45, 0.80 and 1.00, yes. How can we calculate probabilities? Probability function will be calculated here. Distribution function is accumulation, yes? So we will decumulate the values here. 0.15 is here, yes? It's true, but I must calculate now the difference. 45% minus 15%, yes, 45 minus 35 is 0.3. So there is 30% probability, yes, that random variable x will be equal to 150. And again, we must calculate the difference, 80 minus 45, 0.35, 35% probability, yes, that the price of yes, your goods in the supermarket, yes, the spent money in supermarket will be equal to 300 euros, for example, yes, and other difference, 1.00 minus 0.80 is 0.2, 20%, yes, probability is that random variable x will be equal to 500, yes, 500 euros, for example, in our situation. If you calculate the summation through all x, yes, 15 plus 30 is 45, 45 plus 35 is 80% plus 20 is 1.00, yes, so it's true and everything is all right, yes? So this is the probability function of the random variable. Can you see these 35%? 35% is connected with this value 300, yes. So you can see that the mode is equal to 300 euros, yes. This will be the mode, yes. You can calculate expected value and variance and standard deviation at home, yes, if you want. Okay, we will solve this continue random variable. The random variable x is specified by the probability distribution given by probability density. This means that this is continuous random variable. Yes, this is a different situation that we have here a function and the definition range x is higher than 0 and smaller than 1, yes, this is definition range with infinite number of possible values, yes, infinity options is inside this small interval from 0 to 1, yes, and the density, probability density function fx is equal to cx squared, so we would like to calculate constant c so that there will be fulfilled the assumption that the function is the probability density of the random variable x. So we will check our formulas and we will find formula where is written that Newton concrete integral is from minus infinity to plus infinity from fx, yes, the density, according to x, must be equal to 1. Yes, this you will find in your formulas. In our situation, we have definition range. X is higher than 0 and smaller than 1. So our space, yes, minus infinity and plus infinity is between 0 and 1. So what it means? I must use Newton integral from 0 to 1. I must use cx squared. Differential is x, and this must be equal to 1. Because c is the constant, yes, it must be placed in front of integral, which is from 0 to 1. X squared, the differential is x, and this is equal to 1. This is simple function which can be already integrated. So there is c squared parenthesis x powered by 3 divided by 3, lower bound is 0, upper bound is 1, and this is equal to 1. Yes, because this is concrete integral with bounds, lower and upper bounds, we are able to recalculate this difference, yes, c parenthesis upper bound, 1 powered by 3 divided by 3 minus lower bound 0 powered by 3 divided by 3. And this must be equal to 1. Yes? And finally, result c divided by 3 is equal to 1. 3 will be placed here, and constant c must be equal to 3. Yes? So we solved constant c, and we can write that the density fx, the density of the random variable x, is equal to 3x squared. For definition range 0 is smaller than x. This is smaller than 1. So this is your density, and fx density is equal to 0 in all other cases. Yes, this is very important. So we calculated constant c, and there is fulfilled the assumption that this is the probability density of the random variable x. Yes? And because we have the density, we can calculate the probabilities. Yes? Probability that random variable x, probability that random variable x will be higher than 0 and smaller than 0.5. Yes? In your formulas, you can find that this is x1, this is x2. Yes, in formulas you can find that this can be calculated like integral from x1 to x2 from the density 3x squared, and differential is x. Yes. So we will solve this like integral from 0 to 0.5, 3x squared, and differential is x. Yes, I will use another paper, and we can continue. 3 is constant. It will be placed in front of the integral. There is 0, there is 0.5, x squared, differential is x. This is already simple function which can be integrated. So there will be 3 squared parenthesis x powered by 3 divided by 3. Lower bound is 0, upper bound is 0.5. you can calculate the difference between upper and lower bound. Yes, 3 squared parenthesis 0.5 powered by 3 divided by 3 minus 0 powered by 3 divided by 3. Yes, there is 0, this 3 is crossed with this 3, and the result is equal to 0.5 powered by 3. Yes, so this is the result. So probability that random variable x is higher than 0 and smaller than 0.5 is equal to 0.5 powered by 3, 0.125, and this is 12.5%. Yes, so this is probability that random variable x will be higher than 0 and smaller than 0.5. We can continue another probability that random variable x will be higher than 0.75. Probability that random variable x will be higher than 0.75 can be calculated like probability that random variable x will be higher than 0.75 and smaller than 1, because 1 is our limit. Yes, our range is between 0 and 1. Yes? So 1 is maximum. So again, this is our x1 and this is our x2, and we can calculate this using integral where there is lower bound 0.75, there is upper bound 1.0 from the density 3x squared, differential is x. Yes, so we can solve this. 3 is placed in front of the integral. Yes, integral, there is 0.75 and 1. X squared, differential is x. This can be already integrated, so 3 squared parenthesis x powered by 3 divided by 3. Lower bound is 0.75 and upper bound is 1. Yes, and the difference is 1 powered by 3 divided by 3 minus 0.75 powered by 3 divided by 3. Yes, okay, so I will use calculator. 1 powered by 3 divided by 3 minus 0.75 powered by 3 divided by 3, and this times 3. Enter. Result is 0.5781125. Yes, this is probability that random variable x, yes, is higher than 0.75. This is 57.81%. Yes. Why? We have here this result and there we had this result. Imagine that our function, our density, yes, our density 3x squared is power function. Yes, there is our 0, there is our 1. Yes, okay, and integral is a space below this function. Yes, and there we have value 0.5. And when we calculated this value 12.5%, yes, so this space, Yes, this space is 12.5%. Yes, very small space. And now we calculated probability that random variable x will be higher than 0.75, but maximum is 1. Yes, so we calculated this space, and the size of this space is 57.81%. Yes, 57.81% is this space, much higher than this first one. We will continue and we will calculate probability that random variable x will be equal to concrete point, yes, 0.9. Mr. Hellman said to you that probability, yes, I will use this paper, probability that random variable x will be equal to concrete point, for example 0.9, concrete point from infinity options. Yes, we have infinity options from range 0 and 1, so this must be equal to 0%. 0. Why? We can use Newton concrete integral, yes, because this can be rewritten like probability that random variable x is higher than 0.9 and smaller or equal to 0.9. Yes, this is x1 and this is x2. So this Newton integral, yes, is with lower bound 0.9 and upper bound 0.9. Yes, and there we have 3x squared. And differential is x. Okay, so there will be 3 in front of the integral, 0.9, 0.9, x squared, differential is x. This is simple function which can be already integrated, so there will be 3 squared parenthesis, x powered by 3 divided by 3 with bound 0.9 and 0.9, yes? And you can see if you use the bounds, yes, 3 parenthesis 0.9 powered by 3 divided by 3 minus 0.9 powered by 3 divided by 3. There is 0. 3 times 0 is equal to 0. 0% probability. Yeah? So remember, probability that continuous random variable x will be equal to concrete point is every time equal to 0%. Yes? And we can calculate with expected value. Yes, expected value of the random variable x. In your formulas, you have written that expected value is calculated like integral from minus infinity to plus infinity x times fx, and differential is x. Yes, in our situation where we have 0 and 1, our minus infinity and plus infinity, this is equal to integral from 0 to 1 x times our density 3x squared, and differential is x. Yes, we must rewrite this like integral from 0 to 1, 3x powered by 3, and differential is x. And now we can continue with 3 in front of the integral. Yes, 3 integral 0, 1, x powered by 3, and differential is x. Okay, so this is simple function which can be already integrated. So there we have 3 squared parenthesis x powered by 4 divided by 4. Lower bound is 0, upper bound is 1. Okay, we can calculate the difference, yes? 3 squared parenthesis, 1 powered by 4 divided by 4, minus 0 powered by 4 divided by 4. This is 0, and the result is 3/4. 3/4, yes, you can calculate 3/4 like 0.75. So this is expected value of the random variable x. This is the mean, the average, yes. So here, where is this line and value 0.75, you can find here the average, the mean, yes. And if you want to continue, you can calculate the variance of the random variable x. Variance in your formulas, yes, is written like integral from minus infinity to plus infinity. And there we have x squared times density fx, differential is x, minus squared parenthesis integral from minus infinity to plus infinity, x times fx, differential is x, and this parenthesis is in squares, yes? So, can you see what is here? There we have expected value powered by 2, yes? There is second power of expected value. So our duty is to calculate this first part, yes? This first part where we have integral from 0 to 1, yes? X squared times my density 3x squared, and differential is x, yes? So, integral from 0 to 1, 3x powered by 4, differential is x. This is equal to 3 in front of the integral from 0 to 1, x powered by 4, yes? X powered by 4, and the differential is x. Yes, and this simple function can be already integrated. So 3 squared parenthesis x powered by 5 divided by 5. Lower bound is 0, upper bound is 1. And this can be written like the difference 3 squared parenthesis 1 powered by 5 divided by 5 minus 0 powered by 5 divided by 5. I will close the parenthesis. This is equal to 0, and the result is 3 divided by 5. Yes, so the final variance of the random variable x, continuous random variable x, is equal to 3 divided by 5 minus, and there I have my calculated expected value, yes, expected value, 3/4 squared, yes, and if you use calculator, 3 divided by 5 minus 3/4 squared, result is variance 3 divided by 80, and this is equal to 0.0375. So this is the variance, yes? But variance is every time in squared units. Yes, in squared units. We are not able to interpret this result, so better for us is standard deviation. Standard deviation of the random variable x is calculated like square root from the variance. So square root from value 0.0375, yes, is equal to, I will use calculator, square root from this result is equal to 0.1936 and a lot of decimal positions. So this is standard deviation of the random variable x. We will continue with distribution function. Distribution function fx for random variable from range 0 and 1. I will use this paper, yes, and again I will check the formulas, yes. In the formulas you can find that the distribution function fx, distribution function of random variable x, is calculated like Newton concrete integral from range minus infinity to x, and there is function t, and differential is t. This is very important that lower bound is minus infinity and upper bound is x. Our definition range is from 0 to 1, and in the case that we want to calculate the distribution function, we must go only to the middle, so from 0 to x, yes, and there is a very important substitution. Instead of x, we must use t. So please calculate integral from 0 to x, and there instead of x I will use t, 3t squared, and the differential is t. Yes, classical substitution. And now 3 can be placed in front of the integral. There is lower bound 0, upper bound is x. This is t squared, and the differential is t. This is equal to 3. T squared is the simple function which can be already integrated. So there I have t powered by 3 divided by 3. Lower bound is 0, upper bound is x. That can be recalculated like the difference. So 3 squared parenthesis, and now return to substitution, yes? X will be used instead of t. So I have here x powered by 3 divided by 3 minus 0 powered by 3 divided by 3. There is 0. This 3 can be crossed with this 3. And result, distribution function of the random variable x is equal to x powered by 3. This is function, distribution function, so result must be the function x powered by 3, not value, yes? And this function is valid only for x is higher than 0 and smaller than 1, yes? And we must not forget to write here that distribution function fx is equal to 0 in all other cases. Yes, in all other cases, the distribution function is equal to 0. And we will finish this example with calculation of p% quantile, 90% quantile, yes, 90% quantile is calculated on the basis of distribution function. So there I will calculate xp, and this p value is 0.90. Yes, we will use for this calculation the connection with distribution function. Distribution function, yes, in point 0.90 will be equal to this value 0.90. And do you remember my distribution function here? I will use this 3t squared dt as integral from 0 to x 3 t squared, differential is t, and this will be equal to 0.90. Yes, so if I use this integration as result x powered by 3, yes, is equal to 0.90. X powered by 3 is equal to 0.90, and I would like to calculate just x. So x is equal to, I must use third root from value 0.90. Okay, so on the calculator I will write 0.90 powered by 1 divided by 3. Yes, this will be third root. So 0.9 power function, and in parenthesis 1 divided by 3, close the parenthesis, enter. Result is 0.9655. So this value is 0.9655. This value is 90% quantile. 90% quantile of the continuous random variable x. Okay, the random variable is over. We will continue with probability distributions. 10 fair dice, the cubes, will be thrown on the table, and we would like to calculate the probabilities. So what is the fair dice? I will draw here the fair dice. Yes, so this is the dice, yes, and there is, for example, position with value 6, yes. So I know that probability P, which is calculated like small m divided by small n, what I want, divided by all possible cases, yes? So the probability that I will see, for example, this position, yes, value 6, is 1 divided by 6. Yes, if you use the calculator and calculate here 1 divided by 6, you have a probability 0.1666 periodical. Yeah, so this is the probability that you will see what you want. So we would like to calculate probability that on 8 of them on 8 dices, yes, from 10, I will see this value 6. So we know that we will, so this is just the story, yes? So I don't need this story anymore. I know that now I have 10 dices, yes, 10 cubes, 10 dices, and the probability P that I will see what I want is 1 divided by 6, yes. So this is our situation now, yes. So from this information we can conclude that we know 2 parameters, yes, 2 parameters, and 2 parameters using binomial probabilistic distribution. Binomial distribution with parameters n and p, yes. So we have binomial distribution with parameters 10 and 1 divided by 6. 10 is number of independent attempts, yes, 10 fair dices, and this is probability what you require, yes. And we would like to calculate the probability that I will see on 8 dices the value 6. So in your formulas, in formula sheet, you can find probability function of the binomial distribution, which is equal to n above x, which is multiplied by p powered by x, and this is multiplied by 1 minus p powered by n minus x. So this is the probability function of the binomial distribution, and we would like to calculate probability that random variable x will be equal to 8. On 8 of them, on 8 dices, I will see value 6. So this can be calculated like there is combination number n is in our situation 10 dices, yes, 10 above 8, and this is multiplied by p 1 divided by 6, yes, and this is powered by x, this is powered by 8 times, and there we have 1 minus 1 divided by 6, yes, 1 minus 1 divided by 6 is equal to 5 divided by 6, the rest, yes, the rest to 1, and this is powered by n 10 minus 8. Yeah, so you can see it's really easy. I can write here 10C8 because on your calculator you have this combination number, yes. I think that we already calculated this combination number. This is multiplied by 1 divided by 6 powered by 8 times 5 divided by 6 powered by 2. Yes, and the result is the probability. Okay, so I will use the calculator and I will calculate 10 combination number 8 times 1 divided by 6 powered by 8 times 5 divided by 6 powered by 2, and the result is 1.86 exponent minus 5. So this is the result. It's a very small probability. What is it? This value 0.0000186. Yes, if you multiply this value by 100, yes, times 100, you can interpret the result in percent, yes? So in percent 0.00186%. Imagine that you will throw on the table, yes, 10 dices. 10 dices, 10 fair dices, and you want on 8 of them the same number, yes? On 8 of them the same number. It's a very small probability that you will see 8 same numbers and only 2 dices, 2 cubes will be different, yes? So very small probability. Okay, we can continue. Number 6 falls no more than on 3 of them, yes? No more than on 3 of them. So I will use another paper and we will calculate probability that random variable x will be smaller no more than on 3, so smaller or equal, yes, smaller or equal to 3. So what it means, it's probability that you will see 0 dices with value 6, yes, or this is classical OR function, probability that you will see 1 dice, yes, with value 6. Or probability that you will see 2 dices, or probability that you will see 3 dices, yes? No more than on 3 of them, yes? Either 0 or 1 or 2 or 3, but no more, yes? Okay, so this is classical summation, but we must calculate according to this formula. Yes, according to this formula, we must calculate the summation of 4 probability functions. Yes, so probability of 0 is equal to. Okay, I will use this paper here, this probability function. Yes, so 10 above 0, yes, times p 1 divided by 6 powered by 0 times 5 divided by 6 powered by n minus x powered by 10, yes, and you can continue. Probability of 1 is equal to 10 above 1 times 1 divided by 6 powered by 1 times 5 divided by 6 powered by 9. And you can continue. Probability of 2 is equal to 10 above 2 times 1 divided by 6 powered by 2 times 5 divided by 6 powered by 8. And you can continue. Probability that you will see on 3 dices value 6 is equal to 10 above 3 times 1 divided by 6 powered by 3 times 5 divided by 6 powered by 7. Okay, so you have here 4 probability functions. You can use the calculator and you can calculate these partial values. So 10 combination number 0 times 1 divided by 6 powered by 0 times 5 divided by 6 powered by 10. Enter 0.1615. And you can continue 10 above 1 times 1 divided by 6 powered by 1 times 5 divided by 6 powered by 9. Enter 0.3230, and you can continue. 10 above 2 times, in parentheses, 1 divided by 6 powered by 2 times 5 divided by 6 powered by 8. Enter. 0.2907. And the probability that you will see the value 6 on 3 dice is 10 above 3 times 1 divided by 6 powered by 3 times 5 divided by 6 powered by 7. Enter. 0.1550. Okay, so you have here all partial values, and if you calculate a summation, yes, these four values, 0.1615 plus 0.3230 plus 0.2907 plus 0.1550. Enter. 0.9302. So this is the probability that random variable x will be smaller or equal to 3 is equal to this value. You can write 93.02%. Okay, we can continue with the expected number of dices. Yes, calculate the expected number of dices, the cubes, on which falls number 6. So what is it? Expected value. Expected value of random variable x in the case of binomial distribution with parameters n and p. Yes. So this expected value is calculated like n times p. Yes, in our situation, 10 dice thrown on the table multiplied by 1 divided by 6. Yes, the result is 10 divided by 6, and if you calculate this, 10 divided by 6, 1.67 dices. Yes, 1.67 dices. So this is the expected number of cubes of dices, yes, on which you will see value 6. So this is something like mean, like average, yes. And we can calculate the variance of random variable x, variance or dispersion, yes. In different literature you can find dx, yes, like dispersion of random variable x. You can find also sigma squared x. So everything what is written here is the variance. So variance is calculated like n times p times 1 minus p. So this is the variance. In our situation, 10 times 1 divided by 6 times 5 divided by 6. So this will be the variance. I will use the calculator. So there I have 10 divided by 6 times 5 divided by 6. Enter. 1.389. 9. So this is the variance, which is every time the non-negative value, yes? So what is the variance of the number of dice cubes on which falls number 6? Variance is equal to 1.389. Because of difficult interpretation of variance, calculate also the standard deviation. Standard deviation, which can be defined like SD. Yes, we can use this shortcut SD, standard deviation of variable x. In different literature, this is sigma x. Yes, is calculated like square root from the variance. Square root from the variance of this variable x. So square root from 1.389. Yes. So this standard deviation of variable x is equal to, so I will use square root from this value, and the result is 1.179 dices. Because standard deviation, yes, is measured in the basic units, yes. So in dices, the variance is in squared units, and we are not able to interpret this value, this result, yes. But in dices, in basic units, we can imagine, yes, what it means. 1.179 dices, the standard deviation. Okay, so that's all. Okay, do you remember when we calculated the probability that random variable x will be smaller or equal to 3? We calculated the summation of probability that you will see 0 dices with value 6, 1 dice with value 6, 2 dices with value 6, and 3 dices with value 6. Yes? This is just illustration in Microsoft Excel. If you want, you can try to calculate this. Yes? But I showed to you how to solve this manually. You can try to calculate these values in Excel. I draw a picture for you, a picture of the probability function, of the distribution of the probability function of random variable x. Probability that random variable x will be equal to 0, 1, 2, 3, 4, 5, and it's possible to continue. And you can see that the largest values of probability, the largest values are on the position, yes, where is placed the parameter p, probability that you will see the required value. Yes, probability was equal to 1.67. So between 1 and 2, you can find the largest probabilities, and after the probability very significantly limit to 0. Yes? If you calculate probability, that you will see on the 6 dices, value 6, on 7 dices, value 6, 8 dices, value 6, etc. Yes, probability will be very, very, very close to 0. So this is just for illustration. That's all for this seminar. So we continue with probability theory of probability, and random variables. Yes, discrete and continue random variables. And after we started with the probability distributions, and today we started with binomial distribution. Next week we will continue with Poisson distribution, hypergeometric distribution, And after, probably we will continue with normal distribution, which is continuous distribution. This distribution is discrete. As you can see, we have values 0, 1, 2, 3, discrete values of random variable x. So that's all for today. I hope that I will see you next week, and we'll continue with probability distributions, with distribution with names. Yes? So that's all. Thank you for your attention, and bye bye.